this computer. Okay, so if any of the people who are late or don't come want to, they can catch things there. So we can get started. No, it's loading. Oh, that's because I kicked the wrong button again. I didn't mean to click share. I meant to click slideshow. Okay, here we go. Let's see. Today we're going to talk about neural networks, as that's the name of the lesson we have. That's really the same thing as what's called deep learning. People call it deep learning much more frequently today. As it says there on the screen, deep learning extracts patterns from data using neural networks. So when you see the terminology, they're talking about deep learning. It's a question of, I guess deep sounds better than neural networks, but we'll get into what deep means in this context. Areas like natural language and image processing have traditionally been sore points of AI. AI has worked better with computer code and numbers than it does with words and images. And that is what's changing now. It's becoming much more the thing to do things with images. And neural networks and deep learning are the tools that are used for this. The GPT-3 that we've been using is dependent on that, and a lot of image processing that we're going to talk about today. Deep learning refers to certain kinds of machine learning techniques where several layers of simple processing units are connected in a network so that the input to the system is passed through each one of them. This is inspired by the visual information in the brain coming through the eyes and captured by the retina, goes into the visual center in your brain. I would say that our knowledge of how this works in the brain is still quite limited. And you could say that it's inspired by it. You can't say that we're actually copying the brain. What I want to show you here is something from a class at MIT, which it's a very advanced class, I thought. It meets for a week. It meets all day. They have software labs, they have lectures, and the people who take it are people who have been admitted to MIT and have a strong math background. So it's not really something we can follow very well. I've been trying to follow it, and I picked up a lot of their slides. And I'm going to give you a couple of clips from it. This just for a beginning here. We'll go to the introduction.
I'm not getting sound.
Oh, you're not getting sound. Oh my. Okay, that's a mistake that I made, which I often make. So let me stop the share. Okay, thanks for telling me anyway. He was just saying, welcome to the course and so on. You haven't really missed anything yet. But when I go to share screen, there's a little box down in the lower left-hand corner that says share sound. And the default is that doesn't go on. So that is why you're not getting sound. Okay.
Video was actually not real at all. That was not real video or real audio.
Oh, it kept going while I was off, so we have to go back.
Practical guides through these software labs using TensorFlow. Now, I like to tell people that 6S1
Try to get to 120.
you some boring technical answer and description of what deep learning is and the power of deep learning and why this class is so amazing. I'll start by actually showing you a video of someone else doing that instead. So let's take a look at this first.
Hi everybody, and welcome to MIT FitNet 191, the official introductory course on deep learning taught here at MIT. Deep learning is revolutionizing so many fields, from robotics to medicine and everything in between. You'll learn the fundamentals of this field and how you can build some of these incredible algorithms. In fact, this entire speech and video are not real and were created using deep learning and artificial intelligence. And in this class, you'll learn how. It has been an honor to speak with you today, and I hope you enjoy the course.
So in case you couldn't tell, that video was actually not real at all. That was not real video or real audio. And in fact, the audio you heard was actually even purposely degraded even further just by us to make it look and sound not as real and avoid any potential misuse. Now, this is really a testament to the power of deep learning to create such high quality.
Okay. So what did you think? Were you fooled? Did you think that was really Obama? Or I sort of gave it away when I clicked in at one point, but I think it's a shame that they degraded the sound in a sense, because that made it a little harder to hear, I thought. But any reactions at all, or everybody's muted? So
I thought it was Obama.
I did too. I couldn't hear that well anyway.
and
Well,
the sound
I lost a feed for a while, but the little bit that I got, I thought it was Obama.
Yeah, that is something you can do, and they tell you later on. It shows that actually this guy, who was the instructor, made those remarks, moved in that way, and then they're able to paste Obama's features and his voice in and have it duplicate what he did, which is relatively new technology that they're able to accomplish that. And that has to do with what we call deep learning, which we are going to try to understand how it's done. It's not easy, but I think we can do it. So let's get back to share screen. Let me show you something else here. That's another application of this. This is just something I happened to go to. I was in Miami going to art exhibits. I went to Afro Frequency, a multi-sensory immersive exhibit. So this is something new in art exhibits. It's an immersive, interactive digital art exhibit created by Artchos. I'm not never sure how you pronounce that. This is an Afro surrealist digital artist. This is a whole exhibit, was all things done by Africans and Black people who are into this. And what it involves is that you merge in with the image. The images here were African masks. This is Sundiata Keita, who is the founder of the Mali Empire. So he has a mask. This is from the Dragon people. I don't know who that is, but you stand in front of the exhibit and then it mimics your movements, which is a little hard to capture adequately on the computer. But you see me there. This is going to be me holding my cell phone. And I managed to upload these videos. So I think you should be able to see it. Just ignore the sound. That's just random noise in a museum. But you see the mask is sort of mimicking my movements. It doesn't mimic my facial expressions or anything. And you see me holding the phone there. Okay, that's probably enough of that one. I'll just show you the other one. This is a little better video, but you didn't see how it's done. Okay, you don't really get the full experience watching it on on the computer this way. I thought it was impressive, and it gave you a real feeling for the thing. Doing it in the museum, it's life size. It's much bigger. It just shows, I think, that there's a lot of interest in neural networks and digital art. I was also at a number of art exhibits, and they were selling art that was produced by neural networks. Actually, my son is in that business along with other things, and they have a artwork that was produced by their robot, which I can show you probably in a week or two, which they sold. They sold a non-fungible token for $600,000, which I thought was rather remarkable, because what you get is the right to say, I have owned this artwork on a distributed network, but it looks the same to you as it does to anybody else. It's not, but it's sort of like paying money for the autographed copy of a book rather than a regular copy or something. The autograph doesn't really make the book any better, but you feel better. At any rate, the non-fungible tokens is a huge thing in the art world today, and that's a computer thing. I don't know that you say it's artificial intelligence in a sense. So those are things that are going on. What we're going to try to do today is to talk a little bit about how it's done. But let me just make one plug. This is Immersive Van Gogh. Has anybody been to Immersive Van Gogh?
My friends have been. They loved it.
It's
And,
wonderful, I thought. Now, Immersive Van Gogh, it's up in Columbus, and it's hold on. So it's continuing through April and May. So you can buy tickets and go. You know, it's like a video, but the whole building is, the video surrounds you and the paintings come in. I thought it's better than seeing the Van Gogh paintings in the original. Much more of a moving experience. I think Van Gogh probably would have appreciated it. Not that I really know too much about his personality, but exactly how that's done, I don't know the technology of it, but I recommend doing it if you could possibly get up to Columbus. It's not that expensive, and it's not that far, so it's worth doing, I think. Let's talk now a bit about some of the ideas about how these things are done. We were talking last week about regression, which is a statistical technique that plots a straight line on a distribution to try to fit the line, and has remarkable success in doing things, although it's primitive mathematically. It's a very small equation. It's easy to compute. The problem with it is that the world is not linear, or many things are not. A surprisingly number of things are fitted okay. But if you look at this distribution, you can see that some sort of a curve would fit that distribution. Looking at the left one, if you try to fit a straight line, it doesn't fit that well. Now here you have a line that curves and fits the dots, and the neural networks can generate that line. The problem is they're often too good at it, and they overfit. They sort of fit. You can just go from one dot to the other and have a perfect fit. The problem with that is you fit one distribution, and usually you have a desire to use your model in the future with new data. So you want to catch the general pattern, which is here, rather than too much. So underfitting and overfitting is a an issue in these types of models. A neural network involves a large number of simple units, which we call neurons, that receive and transmit signals. When I say a large number, that's a very large number if you're talking about the human brain. You're talking about millions of neurons in the human brain. They're very small. The brain is full of them, and we're only beginning to figure out what they do. But there are two particular things you can say about a neuron. First of all, they connect to other neurons. So when you learn something in your brain, you learn by making connections between neurons in the brain. And the other thing is that when they get input, they store it up until they get a certain amount, and then they send something out. So they send something, they don't just pass everything on immediately. They have an activation function. So that if you just get a little input in your brain, the neurons are storing them up, and then when it gets to a certain point, it shoots them out. And that's really the feature that allows it to be nonlinear. Now, if you look at, this is a simple neural network. The simplest would just be one neuron with an input and an output. This is a one layer. Even with one layer, you see there are 4 neurons here that are feeding into the output layer. And that makes it nonlinear in the sense that they balance each other off. Now, what makes it deep is when you have a lot of layers. So that's where the word deep comes in. So you can see here you have a whole series of neurons, of layers of neurons. And that does seem to be how the brain works, at least certain parts of the brain, and particularly the visual part of the brain, which this is modeled on. It seems that there are layers of neurons, very, very thin, but that things go from one layer to another, to another, to another. It seems that that's true in the brain. Not to say that there might not be a link that skipped over or something. And I don't know much about the brain. I'm not gonna get into that. In your lesson, they have you looking at the neurons in the brain here and learning the names of the different parts. We don't need to know that for artificial intelligence, but there's an exercise for that. What you can say about this brain is that it's dense. This neuron network is that it's dense because everything is connected to everything. Now, sometimes they make them that way, but not always. In many cases, they have limited connections. And it's more of an art than it is a science in the sense that there's not one answer. And the people who work with it keep fiddling with it and adjusting it until they get it to work. It's not very beautiful or impressive on an intellectual sense. It's not like with traditional statistics and calculus, you have a correct answer. And a guy like Newton or somebody thought up the answer for the calculus and how to do it. In this case, you just keep trying till you get something that works, and you keep trying over and over. And that's how it works. And the results are very impressive. If you look at the design of computers, they were not designed for this. Computers were designed according to, this is what's called the von Neumann architecture, which is the design of a computer. John von Neumann was an engineer, worked for GE. He wrote a lot of very prescient papers predicting how things like the internet and so on. But he put together a organization for computers that has an arithmetic logic unit, a control unit, a memory, input and output, different units that do different things. I don't think he was trying to mimic the brain, but you could say that in a sense it does mimic the brain in that in the brain it's sort of like that you have different parts of the brain that do different things, like the parts that's for vision, or the part that's for moving your arms, or the part that's for regulating your heartbeat down here in the stem and the brain stem. And the brain is doing a lot of these things. It does a lot of things at once. Certainly like your heartbeat, you almost have no conscious knowledge of your heartbeat, but your brain is regulating that your whole life. So the brain, in a sense, follows that too. If you look at the macro anatomy of the brain, as opposed to neural networks are looking at the micro. And the link between the macro and the micro is what they don't understand. They're working on it. They're making tremendous progress in neuroscience as they have ways of reading what's going on. That would be a great course for ILR to offer on the brain. I think maybe we did that a few years ago, but not to be taught by me. I'm not the instructor for that, but it's interesting. And we try to mimic that in a sense with the organization of computers, because the brain is an example we have of something that actually works. Neural networks and traditional computers are suited for somewhat different tasks. Okay, the traditional computers are great for tasks where you have a set of instructions and you tell it what to do and it does it. And that's there's a lot of use for that sort of thing. It's gotten to be so common that we don't even think of it as artificial intelligence sometimes. Like if you look at tax software, my wife does taxes as a hobby, as a social service for the AARP. But if you just buy an ordinary tax software like TurboTax, somebody programmed in all of that stuff. It didn't learn anything. It knows exactly what you're told. It's told by the programmer, because that's the nature of taxes. You've got defined laws you've got to follow. Unfortunately, Congress brings them out sometimes a couple of weeks before you've got to publish the software, so that it's hard to keep up with it. But that is very efficient for that kind of task. For playing chess, we don't really have a set of rules that'll guarantee winning chess that you can just follow. We do have now, as we saw for checkers, some games have been solved that way. So the traditional computers are good for things like that. With things that the neural networks are for, we don't really know how we do them. Like visual perception. Looking at this picture, would you say there is one black line or two? How would you figure that out?
I would give you two.
You'd say two. Okay.
I'd say two.
I think I see four ends.
Okay. So
Mhm.
you've got to analyze it. You can't tell that just by looking at it. You don't get that instantly from your visual cortex. You're thinking about it. How many white paths are there?
What was your question?
How many white paths are there going through the thing?
Just one.
Just one path. I
Yeah.
think there's two paths also, maybe. I'm not sure. Anyway, this is the sort of thing that neural networks can work on, and we don't know how they do it exactly. Now, the one thing that they're not so good at is where you have to know the context. Like if you look at the middle letter in these words, they're both the same. And yet we would say that the first is an A and the second is an H. And the reason we would say that is that we know English. So we're assuming that they're English words and therefore we're interpreting them that way, which could be wrong. CHT could be an acronym for some government agency or something. It's not necessarily a word. We don't usually do the word cat in all caps, but you need some of the context to interpret things. And that's something that comes from broader knowledge that we have. And that's what's been hard to give to the artificial intelligences. But they will read things and read handwritten stuff. Like if you have stuff written by hand, who was it that sent me? They're doing the old census from 1950. You got forms that are filled out by hand, right? Who said that?
I did. Shirley.
Okay. So you're not typing it in, you're reading it. The computer is reading the handwritten stuff, I take it.
Yes.
That's not easy. And it depends, of course, on how good the handwriting is, how regular it is, but that's for a difficult task for a computer. And you draw inferences from the context if the handwriting is poor. Now, how does this work? It works through weights. And what it tells you here is that the weights are just like the ones in linear and logistic regression that we talked about last time. So when you look at this nice picture of a neuron, there's no neuron like that inside your computer. You look inside the computer, you won't see neurons. If you look inside your brain with a microscope, you will, brain tissue. All you have is a logic unit. If you're running it on a traditional computer, you have those parts and it's running formulas. You got mathematical formulas, which is down here on the bottom. And that's what they teach you in this lesson here. If we go into how neural networks are built, we have a equation. This is a equation that is not different from not at all different from the regression equations we look at. There's an intercept, which is just a fixed number. Then you say you have a weight, 5.4 times 8, that's the value. Then you have a minus 10.2 times 5. Then you have a minus 0.01 times 22. Now these are the inputs in terms of values, and the first one is the weight. Now you can look at this, you can say which matters the most. 101 is the largest of the weights, so that's the most important value. You multiply the and if it's minus 5, it goes down minus 505 on a couple. Here you see a weight of 0. And that means this variable, we fed it in, but it doesn't make any difference. We could have just left it out. 0 nulls it out. So you can go through and you compute that and you get a number and you shoot that out to the next neuron. And we call it a neuron, but it's really a regression equation. And that's what the exercise here asks us. What is the intercept in this expression? Anybody remember what the intercept was?
10.
Okay, the intercept is 10. We'll go with that. What are the inputs? What did I say were the inputs? Is it 5.4 or is it 8?
5.4.
5.4.
5.4 is actually the weight. 8 is the
Oh.
input. Minus 10.2 is the weight, 5 is the input. So we got to look for one that starts with 8, goes to 5. Okay, so we're going to say B is the input, is the weight. Now, which of the inputs needs to be changed the least to change the output? Which of the inputs needs to change the least to increase the output? Okay, which one needs to change the least would be the one that has the highest weight. This is 5.4 minus 10. Looks to me like
101.4.
101.4 is the largest. So it would look to me like, and that's the what? The first, second, third, fourth.
Fourth.
So I'm going to say fourth. And what happens when the fifth input is increased by 1? Okay, what happens when the fifth input is increased by 1?
Nothing.
Nothing happens because it's multiplied by 0, so that has no effect, right? So we're going to pick nothing. Now we can see how we did. Aha, the answer is correct. And it gives you the reason. So we only got 3 out of 4 correct, so we must have gotten one wrong, I guess. So where's the rest of them? Well, we got to go back up here. This answer is not correct. Which of the inputs needs to be changed the least to increase the output by a certain amount? It says,
That one is correct. It's the one above it, the
the
next
one
one up.
above it is not correct.
That one, yeah. And you meant to pick A, I think, because you wanted the input that started with 8.
I just clicked the wrong number. Well, I just did that to prove that even the instructor can get them wrong, so you don't have to feel bad. And it gives you the answers here. So that's how this works. Okay, now the next thing it talks about is the activation, and that's the nonlinear part. The activation means is how does it decide it's had enough input that it's going to shoot an output. That's the activation. And this shows you a number of different activation functions on graphs. Okay, this one's unanswered. Now, if you look at this, this is a S-curve, as we would call it in techno speak, which is pretty obvious. It starts up slowly, then it shoots up, and then it levels off. And many phenomena in the real world are like this. Like if you're filling a Petri dish with microbes, they'll grow rapidly until they saturate it. World population follows this curve. You know, it doesn't go on forever, it levels off. So if you had an input of 0, you go up here, and over here you get 0.4. Now this is what we call a step. So what did they call this one? They called this one a sigmoid. Sigmoid is a fancy word of saying S-curve in Latin, I think. Okay, a step means that nothing happens until it reaches a certain point, and then it goes all the way on. It's on and off. It's like a light switch. You flick it on and off. And this is the straight linear thing that whatever comes in, it shoots out. So that's the output. Now this one is putting out a slight output here, and then it's putting out a lot more. And then we have questions here. Which of the activations gives the highest output for an input of 5? Okay, so if we have an input of 5 on this one, that's right up here, right? And you're gonna go up to only 1. Okay, it goes from 0 to 1. This one with an input of 5, seems to me it also goes to 1. Now this one with an input of 5, you notice the scale over here is much higher. So if we go up to 5, we'll come out with 4. I didn't draw arrows on these like I did on the other. But if you go up and over, you get the answer. So I would have to say that the identity, the third one, gives the highest input. Okay, the lowest output for an input of -5. -5 here would be -8, right?
-5 is probably -5
What?
first chart.
On the first chart, -5 is going to
Goes to
nothing,
0.
right?
Goes to
And this-
0.
You were,
Am I wrong?
I
Here,
think he started on the bottom chart.
here on the sigmoid, if we go to -5,
0. 0.
it's coming out very tiny
0.
bit above 0. Yeah, that's very low, right? Here, if we go to -5, we're right at 0. You got nothing.
Yeah.
And here, if we go to -5, we're coming out with -6, right? So I would have to say that the identity gave the lowest output.
Mhm.
The highest output for an input of -2.5. The highest input output -2.5 here goes to -4. Whereas this one is at 0. And this one, it's almost 0, but it's not quite. It's a little above. So that would be the highest, wouldn't it? The sigmoid. Okay. So let's see how we did here. Okay, we're correct. 3 out of 3 correct. Okay, so we answered them all correct. Those aren't so much fun as the later one we're going to get to, where we're going to do the neural net. But basically, the idea that it's getting across here is that there are different rules about how a neuron decides to pass on its input to the output. It accumulates it, it sends it out. It seems that the brain does that as well. And that's part of why we do that. And that is something that the programmers fiddle with. So they fiddle with these things when they're working with neural nets. Okay, let's see if we can go back now to here before I'm going to get onto something else, I think. Importance of activation functions. That's what we were looking at. The activation functions introduces nonlinearity. That's what makes it. Now, so here is an example of a linear and a nonlinear result. Here what we have here is red and green dots, and we're trying to separate them. Now, if you try to draw a straight line through there, well, you've got some green and some red on both sides. You haven't done very well. If you want to separate them, you have to have this curly Q ziggity diggity thing. And if that's just a random thing and it doesn't happen every time, then it's not much use. If you have patterns that emerge like that, you're beginning to get a picture. And that's what the activation functions enable it to do. I like this one too, which is a little, a nice graph. I took these from the MIT lecture. You can go through there and hear them talk about them if you're interested. But I like to think of this as a analogy to a wilderness survival experience. So let's suppose you sign up for a wilderness survival experience. They put you in a helicopter and they drop you in the middle of the wilderness and you have to find your way out. And you could say that these are hills. Now, these are actually hills in the data. They're not hills on Gland, but we're looking at it as these are valleys. Here's the lowest spot. That's where you're going to go. Now, suppose they dropped you there. How are you going to find your way out? Let's assume that it's foggy or you're blindfolded. So you have to just take small steps. If you're going to find your way out, you're going to go down. I'm going to think my goal is to go down. I want to go down to get out. So you would say, if I go this way or that way, which one is down? I say, well, this one's down. I'm going to keep going this way. And eventually you find the way out. Maybe it's not real straight, but you find your way to the bottom by going down. Now, if you want to do that mathematically, you can see they have formulas for that. That's what we're not dealing with, but that's what the MIT people deal with, is they look at these formulas and they say, aha, it's all clear. But you have to take a lot of math to do that. Now, the problem here is, what if they put you over here? Where would you end up? You're gonna go down, right? And where you're gonna end up is down there. And you're stuck in a partial lower spot. I forget what you call it, but it's a local minimum. It's not the minimum of the whole thing. So you'll get down, you say, I'm down. I can't go further down. Every way I go is up. But I haven't found my car. I haven't found the exit. I haven't found the trail. I didn't make it. So what do you have to do? You have to try something else. You go up a ways and try going down again. Or maybe you'll go up this way, or maybe you'll go that way, and you make it. And I would think that would be a very frustrating experience for a human, because we go very slowly. But what the programs do is they just keep trying one way or another, and you want to make random jumps. You don't want to just always go down. You want to say, I'm going to try this, I'm going to try a bit of that, I'm going to go that way. You sort of cover the whole thing going up and down. And that would be enormously time consuming if you were stuck in a wilderness area. But it's not very time consuming for the computers. Computers are extremely fast and they can do that. So you have to worry about not getting stuck in a local minimum and make sure you've explored the whole thing. On the other hand, you don't want to do the whole thing on extremely tiny jumps, because that would take too long. You have to pick the right size. You compute the gradient, you go through, and that's what they do. And you find an outlet. Now, the other thing that we do with this kind of artificial intelligence is work with words and try to predict the next word. Like, here is a sentence. This morning I took my cat for, you would predict the next word would be a walk. According to this, that would be your prediction. Though I don't know if people really try to take cats for a walk. Cats are, if it was a dog, that would certainly make sense. You might say, I took my cat to the veterinarian for a shot or something. Now, how does it make this prediction? If you were going to make this prediction, you would say, well, gee, what do people do with cats? And you would guess, well, maybe he took them out to get a shot. Maybe he took them out for a walk, took it out to the basement to chase mice or whatever. What the computer does is it looks through a huge number of sentences, and it looks at what people said after they said, I took your cat out, and it picks one. And it picks what people said more often. And that's basically what the neural network programs are able to do. They're able to look through all of this stuff and look for patterns, look for what people say often. It requires a tremendous amount of computer time to go through a tremendous amount of chats or whatever the words are and search. But that's how they make the models and the programs we've been looking at already, and we can look at some more, is from this kind of statistical prediction. George Banziger has raised his hand. Speak up, George.
Yeah, I just wanted to note the latest version of Word does that. So if I write a sentence, this issue consists, and then they'll anticipate the next word as of, and they'll actually show it in faint print, and then you hit the arrow and it'll enter that word.
If you're using what software, like Word or
Word, yeah.
Yeah, your word processors have this feature. The same thing with Google Docs, which I use, or even on the emails. It'll predict what you want to say. And to some extent, that may be predicting based on your history. Like when I send an email, if I send an email to a couple people in my discussion group, it'll say, how about so-and-so? And it'll pick the people that I previously sent an email to together with the person I put in. So that's what it predicts. It doesn't have it's not thinking about it the way a human thinks about it. It's looking at a statistical pattern, what people tended to say. And sometimes it's right, sometimes it isn't. I find with Gmail, it suggests 3 answers. When somebody asks me a question, like if somebody sends a thing, there's a meeting tonight at 6:30, you can say, I'll be there. Sorry, I can't make it. They'll give you options. Exactly the same technology is used for translation, which you might think is odd. Now, how do they do that? They have a phrase like this: the church men's group is meeting at my house this evening. I can click on Portuguese, which is a language I happen to know, and I get a sentence which is, as far as I can tell, perfect. So it manages to do that. I could also pick on Aramaic, which is a language that my son-in-law knows, coming from Ethiopia, and it'll give me a sentence. I have to take it on faith. Now, how it does this is it has looked through a mountainous number of human translations. And there's a lot of them out there for many languages, like French, for example. In Canada, all of the proceedings of the government are published in both English and French. So they have all of those that can run them through. In the United Nations, you got 5 languages. Portuguese is not one of them, but they found a data set of translated Portuguese to English or English to Portuguese, and they run it through. Now, you can't just run through word by word because languages are more complex. They're looking at phrases and what you're likely to say. In my opinion, they work very well with Portuguese and Spanish. I've had things translated and they look just as good as a human translation, which is probably because my texts are very straightforward. If you use a lot of metaphors and things, it probably doesn't work so well. But translation is readily available for nothing. You got it from Bing Translate or Google Translate, or right on Facebook. If you get something on Facebook, it will ask me if I want it translated. I belong to a group in Lithuania where my great-granddaughter goes to nursery school, or used to go. Now she switched to an English school. But so I get all these posts by people in Lithuania, and I just get them in English. And I would say that with Lithuanian, it's pretty bad. I can't say what the original was, but just the English is sometimes incoherent. I don't think they have a large enough data set of Lithuanian to do a very good job. I'm sure it will improve. And you can volunteer on Google Translate to go in and correct the translation. And if you do that, then they take your input into account. So it's able to do that. That has to do with what we call sequence modeling, which is looking at things in order. You don't just look at one point in time, as you might looking at a picture. You look at them in sequence and how they follow each other. And that gets more complex and requires more and more computer time. Makes more and more difficult. Okay, let me see what this guy is talking about. What we're translating into here is looking at how it analyzes pictures. He just talks about how we code them. We looked at this a little bit already, but let's watch this. I'm gonna go to 3 just for a minute.
So now that we've gotten a sense of, at a very high level, some of the computer vision tasks that we as humans solve every single day, and that we can also train machines to solve, the next natural question I think to ask is, how can computers see? And specifically, how does a computer process an image or a video? How do they process pixels coming from those images? Well, to a computer, images are just numbers. And suppose we have this picture here of Abraham Lincoln. It's made up of pixels. Now, each of these pixels, since it's a grayscale image, can be represented by a single number. And now we can represent our image as a two-dimensional matrix of numbers, one for each pixel in that image. And that's how a computer sees this image. It sees it as just a matrix of two-dimensional numbers, or two-dimensional matrix of numbers, rather. Now, if we have an RGB image, a color image instead of a grayscale image, we can simply represent that as three of these two-dimensional images concatenated or stacked on top of each other, one for the red channel, one for the green channel, one for the blue channel, and that's RGB. Now we have a way to represent images to computers, and we can think about what types of computer vision tasks this will allow us to solve, and what we can perform given this foundation.
Okay, we'll go on to look at that. One of the tasks that we can solve is looking through radiology images. I guess these are on film or digital images, and trying to say what's going on. Looking at your skin and looking at the bumps on your skin. I should show you my wedding picture. If you look at it, I didn't put it up here, unfortunately. You see a black dot on the neck, which I didn't pay any attention to. Fortunately, my sister-in-law, Cindy, who lives here in Barlow, she said, you know, that looks suspicious. You ought to have a dermatologist look at that. So I went to the dermatologist and he said, oh, you know, that looks like melanoma. We better have it tested. And they did a biopsy and I had surgery. So you look at your skin and there's all kinds of things on your skin, particularly if you're not exactly newborn. Some of them look bad and you go to the dermatologist and he says, oh, that's nothing. That's just a blip, blip, blip. Don't worry about it. And then there'll be one little thing and he'll say, well, we got to snip that out quick or it's going to kill you. And that's something that we can train computers to do with these techniques. And you go through and look at things and you decide what it is. And research has shown that the computer is more accurate than a professional radiologist or a dermatologist, depending on whether you're looking at radiology or just looking at the skin. It may be that you just will get a service where you can scan your skin with the camera on your phone and send it in, rather than going into the doctor and having him look at you and see what's going on. Looking at inside of you is a little more difficult, but you find things. Here we have brain tumors. So it's not just looking at pictures of people for the fun of it. It can be interpreting images of this sort that's not common sense because we don't see inside our head. Here is a picture of a head, and I put an arrow here. I believe this is the pituitary gland. This is a tumor on the pituitary gland there. That is prolactinoma. Does anybody recognize this picture? This happens to be me, actually.
Yes,
So if you recognized it, you
I
would
have
know.
one just like it.
Yeah, they gave me this on a CD-ROM after I had it done over at Cooper Hospital. And but the radiologist looked at this and said, whoa, there's a tumor there. You gotta. So I went up to Columbus to a surgeon. If they're gonna cut it out, they're gonna go in through your mouth and cut up through your nose and cut this thing off. But it turned out that since it was a prolactinoma, they can treat that with a pill. Now I had a symptom. I was getting double vision because this tumor was pressing against the optical nerve and I was seeing double. So I knew I had a problem. That's why I went to have this done. Normally you don't just get your see your brain and all of this. So here's all the components of the brain. Probably a typical brain, although I haven't looked at particularly many. I know they saved Albert Einstein's brain, and looking at his brain, it looks like anybody else's brain. So the physical shape of the brain doesn't have anything to do particularly with your intelligence or creativity or whatever. But you can find problems like tumors. Now, actually, they have a lot more than just one picture. They have different pictures. They take at different angles and so on. So it's there's a lot of stuff to go through, and the computers are going to do this, and that can drive maybe some of the neurologists out of a job because it's done by the computer. Breast cancer screening, which is something that women after 50 or so have done regularly. I think you end up with a picture, you look at it, so the computer can go through and look for all these things. This is a case missed by a radiologist, but detected by an AI. AIs don't get bored. That's one of the nice things about them. I think if you look at these all day long, you'd get tired of it. But computers don't get tired. They will go through, they can look at it in detail. And the research shows that they do a good job. So it's useful for that sort of thing. So let's talk a little bit about how this is done. This is a slide that I got from the MIT people, and they're saying you're looking for specific features. Now, in this case, they're looking for the feature of an X. And here is maybe the pure example of an X. You notice there's not very many pixels here. This is like, what, 8 by 8 or something? In real images, it's a whole lot more. The computers can have very fine grained pictures, like that picture of Abraham Lincoln he had. You know, that not very many pixels. You need a lot more pixels to get a good picture. But this is good for us to see. You're looking through, you can see here in the center, you've got the X figure, and you're able to identify that. Now, this is what we're doing in our lesson, the Helsinki lesson, a classifier. It starts with the X, and it calls it a circle, but they admit it looks more like a diamond. And it's trying to identify which you've got. Here it's trying to identify faces as to whether they're smiling or frowning. Well, the frown here is it's going down, the smile is it's going up, but they're not all in the same place. And it gives you the experience of trying to program the network to do that, which is kind of fun. Weights and inputs, we already did weights and inputs. Let's see. We did activations and outputs. This may be in the next section, let's see. Okay, a simple neural classifier. In order to build a neural network classifier, we need to formalize the problem in a way where we can solve it using the methods we've learned. We want to have numerical values. So we will use 1 if it's colored, 0 if it's white. Okay, that's enough for these, although they're in different colors, just not using that. The one that they do down here with this exercise, happy or not, it gets a little more complex. It's got -1. Okay, we'll follow the similar reasoning to build a classifier for smiley faces. You can assign weights to the input pixels in the image by clicking on them. Okay, clicking once sets the weight to 1. Clicking it again sends it to -1. 1 indicates it's for a happy face. -1 is for a sad face. Okay. Maybe if I can make the screen a little smaller here, we can get everything on one here. Oh, okay, maybe that worked. Actually, I think what I want to do is get rid of the top there. Now we can get it into one. Okay. So suppose we want to classify the happy faces correctly. Where are we going to put a 1? Now you could say that the eyes, it's got an eye here, right? But the same thing in the sad faces all have an eye. I don't know if we want to put a 1 there. And we classified 8 of 8 correctly, but none of the sad faces correctly. Okay, because we didn't put a minus there. If we put a minus in there, we got 8 sad faces and no happy faces. So we're really not getting anywhere with that because it's the same in both. Now here we have something coming up. A couple of them do have, so we can put a plus. Suppose we put a plus in here and a plus over here. We've caught 2 of the happy faces and none of the sad faces. So what are we going to put in for a sad face? We're going to go down here, put in -1. Okay, we only got 1 of 8 happy faces and 2 of 8 sad faces. Okay, how are we going to do next? What are we going to put in here? These? If I put pluses in here, I can get 6 of 8 happy, but only 1 of 8 sad. Okay, you can fiddle with this all you want, and you're not going to find the answer. That's what they're trying to tell you here. There is no solution that gets 8 of 8 of each. You have to break it down more or do something more complicated, do something more advanced. And that's where we're getting into the advanced techniques. And the advanced techniques, it really just talks about, it doesn't have you practice them, which is, but the advanced techniques are pretty difficult to do or to even understand, but we're going to do our best here. Now, gotta get to go back here so I can go back over here. High level feature detection. Okay, now what they do is they look at features that tell you it's in a certain category. Like there are 3 categories here: houses, cars, and faces. And if you have a face, you're going to have a nose and an eyes and a mouth. Now you also have a rather prominent hat here, but that turns out to be accidental. You may or may not have a hat. With a car, you may have a license plate, headlights, wheels. Once you see some of these things, you have certain key features that you look at. And I think that's how our brain works. If you look at a picture, these are such good pictures that you see it instantly. If it's foggy, if it's a poor picture, you may have the experience. You look at something, you can't figure out what it is, and then it clicks in your head. Oh yes, that's a car, and then everything sort of makes sense. So that's what they're training the computer to do, to become familiar with key features. And usually each of these features is a layer of neurons. So you've got many, many layers, and you can have hundreds of layers. You don't have to have just a handful. Now, as a result, you can generate faces. These are a sample of faces that they generated. So once you get this collection of features, you can then put them together into a result, and you can get made up characters that look like a regular picture that somebody took with a camera. Now, how do you learn feature representation? You start looking for low-level features, you go to mid-level features, high-level features. So there's layers, and each of these layers are different layers of neurons. And what they do is they go through bit by bit. This is where you get into what we call a convolutional neural network, which is a fancier term for saying that you're going to look at it bit by bit, and you're going to see where you find certain features. And you're looking for certain features. It's like George raised his hand. Look at that. It clicks through and tells me you raised your hand. You're very polite, George. Just speak up. It's a small
Yeah.
group.
Would a AI computer do better at recognizing a human face with a COVID mask, or would a human?
Well, you could train it depending on the data set you trained it with. If you trained it on faces with COVID masks, it would look for the COVID mask. And I think it would, whether it would know that the COVID mask wasn't part of the face and could be taken off. So it's trained on a certain, it depends on the data set you train it with. Now, you don't think about it in the way that a human thinks about it, how that's a mask can be taken off. It's interesting when you look at things like when the first Spanish conquerors landed in Mexico, they were riding horses. And the natives thought the horse and the man were a new animal. It was all combined. It was one thing. So pretty soon they figured out, the man can get off the horse and the animal are two things. And I suppose a computer can learn that, but it's going to learn based on what you feed it. And you have to feed it an awful lot. Identifying somebody, you get into this with trying to identify faces, with putting up a picture of somebody's face and finding who they are, which the police can do now. We don't have access to those data sets, at least that I can find. But you have to have a tremendous body of data to do that. I am going to cop out on this and let this guy explain convolutional neural networks to see if he makes more sense than I can make.
Okay, pop quiz. What am I drawing? I'm going to make 3 predictions here. Firstly, you think I drew a house. You'd be right. Secondly, that it just came really easily to you. It was effortless. And thirdly, you're thinking that I'm not much of an artist. And you'd be right on all counts there. But how can we look at this set of geometric shapes and think, oh, house. If you live in a house, I bet it looks nothing like this. Well, that ability to perform object identification that comes so easily to us does not come so easily to a computer, but that is where we can apply something called convolutional neural networks to the problem. Now, a convolutional neural network, or a CNN, is an area of deep learning that specializes in pattern recognition. My name is Martin Keane, and I work in the IBM garage at IBM. Now, let's take a look at how CNN works at a high level. Well, let's break it down. CNN, convolutional neural network. Well, let's start with the artificial neural network part. This is a standard network that consists of multiple layers that are interconnected, and each layer receives some input, transforms that input to something else, and passes it output to the next layer. That's how neural networks work. And CNN is a particular part of the neural network, or a section of layers. Let's say it's these 3 layers here. And within these layers, we have something called filters. And it's the filters that perform the pattern recognition that CNN is so good at. So let's apply this to our house example. Now, if this house were an actual image, it would be a series of pixels, just like any image. And if we zoom in on a particular part of this house, let's say we zoom in around here, then we would get, well, the window. And what we're saying here is that a window consists of some perfectly straight lines. Almost perfectly straight lines. But you know, a window doesn't need to look like that. A window could equally kind of look like this, and we would still say it was a window. The cool thing about CNN is that using filters, CNN could also say that these 2 objects represent the same thing. The way they do that then is through the application of these filters. So let's take a look at how that works. Now, a filter is basically just a 3x3 block. And within that block, we can specify a pattern to look for. So we could say, let's look for a pattern like this, a right angle in our image. So what we do is we take this filter, and it's a 3x3 block here. We will analyze the equivalent 3x3 block up here as well. So we'll look at, first of all, these first group of 3x3 pixels, and we will see how close are they to the filter shape. And we'll give that a numeric score. Then we will move across 1 column to the right and look at the next 3x3 block of pixels and score how close they are to the filter shape. And we will continue to slide over or convol over all of these pixel layers until we have mapped every 3x3 block. Now that's just for one filter, but what that will give us is an array of numbers that say how closely an image matches our filter. But we can add more filters. So we could add another 3x3 filter here, and perhaps this one looks for a shape like this. And we could add a third filter here, and perhaps this looks for a different kind of right angle shape. If we take the numeric arrays from all of these filters and combine them together in a process called pooling, then we have a much better understanding of what is contained within this series of pixels. Now that's just the first layer of the CNN. And as we go deeper into the neural network, the filters become more abstract, or they can do more. So the second layer of filters perhaps can perform tasks like basic object recognition. So we could have filters here that might be able to recognize the presence of a window, or the presence of a door, or the presence of a roof. And as we go deeper into the CNN to the next layer, well, maybe these filters can perform even more abstract tasks, like being able to determine whether we're looking at a house, or we're looking at an apartment, or whether we're looking at a skyscraper. So you can see the application of these filters increases as we go through the network and can perform more and more tasks. And that's a very high-level basic overview of what CNN is. It has a ton of business applications. Think of OCR, for example, for understanding handwritten documents. Think of visual recognition and facial detection and visual search. Think of medical imagery and looking at that and determining what is being shown in an imaging scan. And even think of the fact that we can apply a CNN to perform object identification for badly drawn houses. If you have any questions, please drop us a line below. And if you want to see more videos like this in the future, please like and subscribe. Thanks for watching.
Okay. Maybe that was all clear
Pop
now.
quiz. What?
Maybe not. But if you want a more detailed explanation, you can go into the MIT course, and And then if you want really more, get admitted to MIT and they have a software lab and so on. So you go on. The things you can do with this is combine your picture with somebody else's picture, change how you look, create new people. So this is beginning to get out there in terms of commercial software. If you look here, these are the real people. These are the different models, and you could say, take my picture and make me look more like this model, and then you end up looking like that. So that's something you can do with an image if you care to do that. There's a software called FaceApp, which is available for doing that. And I thought we could take a look at that. If you look at this, you will see that I have created a second image of myself. I simply did this by opening up Zoom on two different computers. It's not any artificial intelligence. It's not because I have a divided personality or something. I want to show you something that runs on the Chromebook. It doesn't run on the PC. So I'm going to show you the Chromebook screen. Let me see now. If I go into share screen here, multiple participants can share. All right. So I should be able to go into my other identity here and decide to share my screen. Let me see if I can do that. Yes, I'll share, I guess, my desktop. Oh, maybe I share an app, actually. I get a choice of sharing an application. Okay, I'm going to share the FaceApp. This is FaceApp, which is a free program that anybody can subscribe to. It edits photos. Now it's looking through a bunch of things on my file that who knows where they came from, but you can take your picture right with FaceApp. You have to use a phone or a tablet. It doesn't run on a PC unless you have a program that simulates Google Play. So here's a picture I took of myself. I just took that with the app because I wanted a picture that's not anywhere on the web or anything. I'm trying to use this picture to search too, using another software we're going to demonstrate. And then I can make some changes. So I can go down here to gender and I can click and say, which would I like? Now, suppose I want to be female. I can go here. And guess what? That's what I look like as a female. Is that good? I don't know. Do I look better as a female or a male? I have no idea. I don't, not bad, I guess. I don't look so, I'm not so great looking either way. Here is, I put on masculine. I don't think I look any different. I think I already looked masculine. I didn't really do anything to me. If I go over here to original, I think original and masculine are the same. There are two different female. From what I've read, that females always get long hair. That seems to be how this is built. So it's taken my features and meld them in with its image of what a female looks like. Okay. Now then, suppose I'm not smiling, I want to go with smile. Now you notice that the trick here is that these are all for the Pro version, which means you pay money. So you can pay for a subscription, but I can take the original smile here, and there we go, I'm smiling. So it changed my image at least to smile. And Oh yes, what if I had a beard? I only get one full beard option. Say my beard would be white, believe it or not. And that's actually true, although my hair is not white, my beard turned white 20, 30 years ago. That's when I shaved off my beard, actually. I looked younger without the beard once it turned white. So there's what I look like. And this is simply a free software. Now they are saying this is, if you're going to edit pictures, you can use this and save using the photo ops software where you do it. Like if you're a commercial photographer, you take somebody's picture, you can doctor it up with this software a lot quicker and easier than using the softwares that people usually use where they do it themselves. Changing somebody's picture to give them a smile, I think that would be very difficult to do if you did it in your own software. Here, suppose I wear makeup. See if I would look better with makeup. Doesn't seem to be much of a difference, does it? I wonder if I could go to female and then apply makeup. I'd have to save this picture. I can save this picture. Well, now that I've saved it, it doesn't mean that I'm able to process it. And probably can if I'd have to go back to the beginning, I guess, and see if they have it.
Try the apply button in the lower right.
Apply button in the lower right, not a, oh, what?
Make yourself back into the female. And then in the lower right-hand corner, it says apply.
Okay. I'll try that.
Maybe you can keep that and then move on.
Well, it looks like I can edit it. Yeah, it says apply. And I've got the choices here. So I can apply some makeup. Does that make me a more attractive female? I've got lipstick, right? I think that's definitely an improvement. Now I'm going to take this picture and submit it to one of the dating apps and see how many hits I get with this picture. So you can play around with this. This is free. This is available to anybody. It's called Face App. But I say you don't put it on a PC unless you have a Google Play simulator, which is a whole nother step. But you do it on your phone, or you do it. I'm doing it here on the Chromebook. You can do it on an iPad. So you can go through and modify pictures. And there's other choices in there. You can make yourself look like Brad Pitt or like a celebrity. They have celebrity models, and you can click on that and make yourself look more like the celebrity of choice. Probably you can download other pictures yourself and do it. I have little experience with this, but there we go. I think I'm pretty good looking there. That's good. Okay. So that's an example of something you can do using this sort of, they say they're using artificial intelligence. Of course, they don't tell you exactly how they're doing it. It's not like this is all proprietary stuff. I only have one personality, so I think I'm going to leave the meeting as my second personality and just have one window. We only have limited bandwidth here. Running 2 is putting a strain on the system, but that's something, it's fun. At least you can put it on Facebook, show people what you look like as a woman, or if you're a woman, show what you look like as a man. We have more women than men in the class, so you can go either way. That's a software you can use. Another thing you can do is to transform speech. And it tells you how you go about doing that. We can't practice, but they make it into audio waveforms. And then you could say, make me talk like somebody else, such as Barack Obama, which we saw in the video at the beginning. They take the words that the instructor from MIT spoke and transform it so that it's expressed in Obama's voice, and probably pretty well, in the sense that they could do better than they actually did. For some reason, they thought they could be accused of some sort of scheme or something if they did it too well, so they degraded it. But you can come up with pretty good sound. Now there's software that I found you can buy for doing voiceovers. Like if you wanted to produce a video, often you have a voiceover in the back. You can type it in and it produces the sound for you with a professional voice. Saves you the cost of hiring an actor to read aloud your script. The actor can read aloud your script pretty well. Instantly transform any text into 100% human sounding voiceover with only 3 clicks. I think you had to pay for this one. I don't think there was a free sample, so I don't have an example. But we can find this in a lot of places. Actually, I should be doing this in a different browser if I'm going to do this. So let me stop the share here and open, because I didn't install this on Chrome.
Ted, are there any laws governor, I can't even say it. Are there any laws about this? I mean, can anybody go on and talk like Biden or anybody?
I'm not aware of any law against it. I mean, if you did it for fraudulent purposes, it would be illegal. If you tried to call your bank and say, I want to change the password on my bank account, and this is Ted Gertzel, and now you might say, you know what, when somebody calls on the phone, you recognize them by their voice, right?
Yes.
You know who you're talking to. That may become very questionable, because what they would have to do, they would have to have a large sample of your voice, and they would go through and make a model of it using this kind of software. And then they could transform their words into that voice. And it could sound very much like the real person. Obviously, that's illegal if you did that for fraudulent purposes.
So there are laws.
Well, there are laws against fraud. I don't know that there's laws against doing that. But you saw there on the video from MIT, he said they purposely degraded the video so that it wouldn't seem real, and they told you this is not real right there in the projection. So clearly they were worried about that.
Okay.
They were worried that they could be accused of something. I have not heard that there's any law specifically against doing this. I think you're allowed to do it. But it's, you know, I've seen this in science fiction where somebody can change their voice like Data in Star Trek and talk like somebody else. It seems like we're getting the ability to do that. You know, just all I would have to do is talk and run it through the software, and this would sound like somebody else, which is, it opens up possibilities. As far as I know, legislature has not got around to passing laws against it. They're more concerned with picture recognition and stuff. And they are
Yeah.
with that.
Okay, thanks.
If I can get this to, okay. I'm just opening up here. Now I'm gonna go back in, and I had to put this in a different browser for this to work. Share screen again. And we'll go here. This is an article that I'm recommending that we're going to talk about next week about AI is mastering language. Should we trust what it says? This is in the New York Times. I've also put it up on I put it into the Google Docs, but I don't seem to have gone to that. But let's see.
Omitted the very last word of the first. The missing word jumps into your consciousness almost unbidden. The very last word of the first paragraph. There's no sense of an internal search query in your mind. The word paragraph just pops out. It might seem like second nature, this filling in the blank exercise, but doing it makes you think of the embedded layers of knowledge behind the thought. You need a command of the spelling and syntactic patterns of English. You need to understand not just the dictionary definitions of words, but also the ways they relate to one another.
Well, what I would just demonstrating here is the read aloud function that is now built into Microsoft Edge. Chrome, if you use that browser, you have to install an extension to get it, but they have the extension, so it's available. Now, there's been software for reading text aloud before. I have it on the Kindle, and you could always tell that it was a machine reading it something aloud. It didn't sound like a human. I think with this, it sounds pretty good, don't you? It sounds as if you got a person to read
Another,
it aloud.
you have to be familiar enough with the high standards of magazine publishing to assume that the missing word is not just a typo, and that editors are generally loath to omit key words in published pieces unless the author is trying to be clever, perhaps trying to use D to understand not just the dictionary definitions of words, but
Okay, so that's a, a service that's available. I think it's a great boost for people who are visually impaired. Clearly, you would be able to pull up anything and read it aloud. There's been software for that before, but it's not been as good. So it's basically better at doing it than we've been able to do it in the past. Okay, another thing I tried doing was searching for myself, which is let's see, I was actually on Google when I did that, wasn't I? Let me open Google as a browser. I guess I still have it open. Okay. You could go to image. I think that's what you go to, if I can remember. You can go to Google Image and you click on
That's
this
not what we're
camera.
seeing, Ted.
You're not seeing it?
We're not on Google.
I'm on screen share on, you're not seeing the screen Google share, Google Images?
No, we're seeing screen, or it's slide 42 is what we're looking at. A little picture of you and some
Oh,
information.
okay, we're over here. Maybe I've got too many things open here. Let me just go back to close that. All right, this is here. Okay, this is Google Images here, right? Are you seeing Google Images now?
I see
Yep.
Google Images.
Okay. Let me try to find the image. Choose file. If I can remember where I put this. Images, that's a clue. But that's not the one that I just took. That's an image that's already been on the internet, which is not as good, but let's try this. This is a friend of mine who committed suicide 30 years ago. I have the picture of him on here. What it does is searches through and looks for other images that have to actually be identical, the same picture, or else it doesn't find them. They think he looks old, and he's not so old. He was only 50 some when I took that, but, and then they'll give you images of other people that they think look similar, which I didn't find to be that that impressive. That seems to be the state of the art that's available for this now. There is this commercial one. You go in and they claim that they're doing all sorts of searches of social media and everything. It takes about 3 minutes and then it runs. Then they want you to pay $5.99. And I'm sure they're going to give you, they've got 53 matches for me. That means 53 possible matches are people who look a little bit like me, which is nothing special. I'm not that unusual looking a person. And, you know, they're making a thing where they're making money out of it. I wouldn't pay money for it, so I don't know how it works. Okay, I got some more things here, but I don't know that we have time for them. We did convolutional neural networks already. There's one other topic in our lesson. Let me just see if I can open the lesson easily. Do I already have it open? I already have it open. Okay, here they're talking about GPT-3's neural network. I'm in the New York Times. I'm not in our lesson. Advanced neural network techniques. Okay, convolutional neural networks, that's what we saw the video about. I think their explanation here is better than anything I've seen anyplace else. So if you want to read something about convolutional neural networks, I would recommend going right to our Helsinki lesson. It's just something to read. There's nothing to do about it. The one other thing that I wanted to introduce was generative adversarial networks. This is part of how they create the pictures. And this is another very clever step, which is described here. There's nothing we can do to experiment with it. What they do here, it's sort of like a Turing test between two computers. They start with a computer that is generating images in the way that we talk about it. That's what you mean by generative. And then you have another one that's putting up real images, and the computer is challenged to pick which is real and which is false. So it's sort of like the Turing test, where you're trying to distinguish the real conversation from the false conversation, except that it's with images. And it's done completely by two different AIs that become adversaries and argue with themselves. And the purpose of this is that the computer program that is generating the false images keeps getting better and better and better, so that it can win this competition until it gets to the point where it's doing as well as the real, and you're getting the analytical software is choosing the false images as often as it's choosing the real images. And that is what we call an adversarial network. These are some of the images that were created and that they have here in the Helsinki lesson. And it's, I don't think, looking at them, we would say that these were false, just using what ability we have to analyze things. Now, maybe if we had some sort of software and went pixel by pixel, we could figure it out. But the above images were developed by a generative adversarial network. So that's an example. So that is the final twist that I wanted to mention, of creating an adversarial relationship between two AIs in order to train one to do better and better, so that it can win the competition. It's not something that we can practice, but it shows how they develop the software. It's a common thing in software development, what we call evolutionary modeling or generative modeling, where you throw out lots and lots of things and you pick the one that works best. So it's like the survival of the fittest, except that the survival is the survival of computer programs rather than survival of biological organisms. And so that evolutionary development can go a lot faster than it does in biology. Okay, so we've had an overview here of neural nets and deep learning. We've got some idea of the technology of it and some idea of how it is used. What I want to do for the next two classes is talk a bit about the implications, the uses, what's being done. There was that article from the New York Times that I recommended, that's from the magazine, which is a discussion of particularly the GPT-3, the writing apps, what implications it's going to have. There's a lot of other things. So if you feel like reading something that's worth reading, I put a link to that up. I'll put that on the syllabus somewhere. So I put it there in Drive, so you don't have to have a Times subscription to get it. There's a lot of other discussion about this. I may ask my son to see if he can join us next week or the week after, because he is really at the cutting edge of this stuff and has a lot of strong opinions about it. Which are controversial. He's sort of on the fringes of a lot of things. So we'll have that sort of discussions next week. There's not really any more technical stuff that I plan to try to introduce. The learning to do generative, adaptive, adversarial modeling or that sort of stuff is beyond our capabilities. You have to go to enroll at MIT and take that course and go to the software lab and so on. But we have a feeling for what it's about. And if there's any things that you're particularly concerned about or would like to talk about or whatever, let me know and we can look at things. There's a lot of implications of these things. Anybody have anything else they want to bring up or?
Sure,
Yes,
Ted, I have two examples of things that relate pretty closely with what we talked about today. One of them is called Snapchat. You guys, if you have grandchildren, you may be familiar with it. It does what FaceApp does, but it takes it kind of to an extreme and you can become a monster or part of a cartoon, or it can warp your face into crazy shapes. And it's actually really fun to use. And I share Snapchats with my 88-year-old mother-in-law on a regular basis. And we have a pretty fun time making silly representations of ourselves and sending them back and forth. So, and it's fast. You can do it on your phone. You can download the app for free. And it's the same kind of technology that the Face app does. And the other thing that I have on my phone, it's an app called Lens. So if I'm outside and I see a flower and I don't know what it is, I can take a picture of the flower and then share it with the Lens app. And the Lens app will look at the flower image in my photo and it will help me identify what the flower is. It's not always exactly right, but if you really have no idea, it can get you going along the right path and figure out what it is. Now, I've never tried that with a picture of a person's face though, so maybe I can try that. And it would be the same thing as searching on a Google image for a face. But I use it for plants and birds and animals all the time. And it's kind of fun. It's another free app on the phone.
We had the
Have an
bird
app.
watching course and we could have used something like that. I don't think they're making it available to do face search for people. That would be a legal issue. And even when the police do it, there's legislation has been proposed to prohibit them from using search to find people and so on. So that is probably not available anywhere that you could actually find a person unless you have an image that's already on the web somewhere, then it'll tell you where else it appears.
Yeah, I have a similar app, Plant Snap, which identifies plants. And then I have, I believe it's out of Cornell for birds, the Cornell.
Merlin?
Merlin, that I use. That's pretty good. None of them are perfect. I find that they sometimes get it confused, but they're fun.
But if
Yeah,
it's
they are
wrong and
fun.
you correct it, you feed in information, it will improve.
Yeah.
So that's how
It
they
asks
all,
if this information was helpful and you can check yes or no.
it doesn't say, can you improve the identification or something? With Google Translate, it asks you to improve the translation. And you can sign up to be a regular participant. They like people to translate, but I don't know with birds. There are people who know a lot of birds who could have helped to improve their identification, I'm sure.
Yeah, there's actually a program called iNaturalist, and you can put in a picture of a flower or a bird or an animal and where you are and what you think it is, or you can ask, what is this? And naturalists who are on that app all over the world will look at it and you'll have information in a matter of moments on what that is, whatever it is.
So that's crowdsourced. That's going out to the participants. Okay.
Yeah.
Well, I'm
So I
glad to have
just
you
did a
bring things
lens.
and share them with us, and you can demonstrate them a bit on during class if you're willing to do that. I can open screen share for anybody to screen share.
I don't know how to do those
I don't
if it's
either.
not on my phone.
I don't either. Louise, what was the name of that naturalist? The naturalist?
iNaturalist, little I, and then
Oh,
the word
You don't do it
naturalist.
on the computer, you do it on the phone.
Yeah,
Yeah.
that's
You
all.
can do Zoom on the phone, but you can screen share with Zoom on the phone. I'm not sure. You can install Zoom on your phone. That's not a problem. I'm not sure whether you can share the screen on a phone. That I've never tried to do.
I don't know.
There's also a way to project your computer onto your PC screen. You have to install software for that if it's a Mac, if it's Windows. On a Mac, it's included in the Mac. So you can do that. That's why I got the I used the Chromebook here to show you the Face app, because it runs on that, but it doesn't
Mhm.
run on the PC.
Hmm.
Now, what effect is this having on people? What effect do the dating sites have? We can look at that. There's an article in the New Yorker about that probably a week or two ago. I don't know if you realize this, but sex is declining. It's not increasing. People are having less. There are more people who report they didn't have sex for a whole year than there used to be. Particularly among young people. It's not just among people get older, they don't have as much sex, but there's a decline in teenage pregnancy. So it's not necessarily a bad thing that people are having less sex, but is that an epidemic of loneliness? There's a book out that's saying people are all lonely because they're sitting on the computer and they're not relating to people. And of course, that's tied up with the pandemic, and we're lonely because we're afraid to go out and catch something from people, which is people are giving up on that now. I'm probably going to catch more as a result, but we mentioned vaccines, by the way. I went down to Rite Aid and walked right in. They just gave me a vaccine, COVID booster right away. I think you can go to any pharmacy and just walk up to the counter and get one. Gave me a choice of Moderna or Pfizer, whichever you want. So they're available.
Is that the fourth one,
Yeah.
Ted? Okay.
Yeah, I brought my
good.
card and he looked at it. He typed a whole bunch of stuff in the computer, so I assume he checked the registries or whatever, but
Good.
it have to have been a certain amount of time since your third, I think. If you meet the medical qualifications for it, it's available. Okay, I'm going to sign off. I'm going to see George is coming, I guess, to the men's group. We have the men's group at the church. So I'll be seeing George after a bit in person.
Well, you have fun. That sounds good.
I hope to. I've got to get.
Today was so interesting, Ted.
Thank you very much.
Thank you
Okay.
very much.
Thanks, Ted.
Okay, we'll see you next week.
Thanks, Ted. Thanks, Ted.
Thank you.